happens to be our first sheet on magnetic effect of current. I'm assuming you would have attempted problems from the sheet because I had made a request that you come a little in advance and have a look at these problems so that we could save some time in the class, right? So let's start examining problems from the sheet then. About it. So the first problem, which is about a sphere of radius r falling vertically under gravity from a height h, starting from rest, in a region of uniform B going into the plane of the board, and it falls on a surface, a very large surface, conducting plane. This is a large conducting plane which is maintained at V volts, The sphere is metallic as well, therefore conducting, right? Now when this Johnny falls on this, by the time it reaches this, it would have acquired a velocity, right? So when it falls, let's say it acquires a velocity v naught equal to root 2 gh, right? Now this is initially uncharged, even though it's in contact with this plane for a very short time, but being highly conducting, it exchanges charge with the conducting plane to such a degree that their potentials get equalized. That's an assumption that we are going to make during our computations, right? So when it falls on this, let's say on the conducting plane, it acquires a charge q from the plane such that kq by r, that is q by 4 pi epsilon naught r, that's the potential to which it gets raised, and that must be equal to v volts, that of the conducting plane. The conducting plane being so huge that some loss of charge from the conducting plane will not result in change of potential of the plane, right? That's a good approximation. So then q is obtained from these considerations. So q is 4 pi epsilon naught r into v. That's the charge that collects on the sphere during that short time of contact with the conducting plane. Clear? B is into, it has a velocity v naught like this. Then you very clearly know, if you have to calculate the radius of the circular path that it would assume right after that, it's going to be mv by qb. mv naught, that is mv naught velocity divided by q that we have calculated into b. That would be the required radius right after impact. Got me? Now the next problem. So far so good, right? Pretty simple? Yeah, C is yes, 4 pi epsilon naught r. Absolutely, no problem with that. I mean, perfect. For an isolated sphere, C is 4 pi epsilon naught r. Right, right, same thing. Can I wipe this off? The second problem, in which there is a region of magnetic field which is time dependent magnetic field in a certain region. B is B naught e power minus lambda t. Time dependent magnetic field in a certain region. Okay. A particle enters this region perpendicular, so this perpendicular to the B. It has a velocity perpendicular to B. That's how it enters. Charge Q, mass M. Now, what would happen to the speed of the particle as it migrates through this region of time-dependent magnetic field? What will happen? Yes, time-dependent or space-dependent. Magnetic field is incapable of changing the kinetic energy. Therefore, the speed will remain constant. It will be time-independent. Right? Yes or no? It will not depend on time. The speed will remain the same. The magnetic field all by itself is incapable of changing the speed and the kinetic energy of the particle. So, speed would be time independent. Yes or no? Right? And therefore, option D, option Delhi, none. Clear? Two particles A and B with identical charge to mass ratio lambda. Two particles with the same charge to mass ratio lambda. A magnetic field B exists perpendicular, let's say, to this plane. There are two particles, particle A that has a velocity, say V, and particle B which is initially at rest at this point. Right? Now, forget B. Had it been for A alone, B into the plane of the board, right? B into the plane of the board, it will execute a circular, or let's say out of the plane of the board. So, so it will execute a circular trajectory. Yes or no? See, if assuming Q is positive, V is like this. If B was like this, V cross B would have been upwards. Okay. If B was out of the plane of the board, then V cross B would be downwards, and the center of the circle will be here, and the circular trajectory that A would have proposed would be this. This would have been the circular trajectory proposed by A. If there was no collision with B, it would have executed a circular trajectory of this kind with radius R equal to mv by qb, with angular velocity omega equal to qb by m, with time period t equal to 2 pi m by qb. Yes or no? Right? Now, B sitting at rest and A undergoes a perfectly elastic collision with B. If two particles undergo a head-on perfectly elastic collision, what happens? Their velocities get exchanged. That means after collision, B picks up the velocity of A, B picks up the velocity of A, and A comes to rest. A comes to rest. This is what happens. B then executes this circular trajectory. B then executes this circular trajectory. It comes to this point, hits A, and then A takes over. So alternately, A and B execute this circular trajectory. One particle idles, the other particle executes a full circular trajectory. Yes or no? Now, look at A. Say, when it has given away the velocity B to B and has come to rest, what time B takes for a full revolution? This time, which is like Q by M if you take as lambda. This is 2 pi by lambda B. In a time equal to 2 pi by lambda B, A is idling. A is idling. Yes or no? Now, in the next capital T seconds, B idles and A executes a full trajectory, circular trajectory. Yes or no? That means, if you look at the complete cycle of A, it idles for capital T seconds and then executes a full circular trajectory for capital T seconds. That describes the nature of motion of A. Yes or no? So, if you think about the period of A, it's 2t. 2t. 2t, yes or no? 2t will be the period of A, because capital T seconds it idles and capital T seconds it executes a full circle, and then it idles for capital T seconds and 2t. So then the periodicity of motion of A is 2 times t, not t. 2 times t means 4 pi by lambda would be the periodicity for A, because it idles for capital T seconds and then executes a circular trajectory for another t seconds. So to examine the motion of A completely, you would have to look at a span of 2t seconds, which represents the periodicity of motion of A and also that of B. So the time period of motion of A or B is going to be looked upon as 2t. It idles for capital T seconds and moves for capital T seconds. This is how it is. So which makes it 4 pi by lambda. That will become 4 pi by lambda. Clear? Problem 4. There is a current carrying wire placed along the y-axis. It could be carrying current either in the plus y direction or the minus y direction. Clear? We do not know whether the current carrying wire is carrying current upwards or downwards. That's not known to us. But what's known to us is the value of the magnetic field at a point 0, 0 d. That means what's known to us is the magnetic field at a point. See, z-axis will come out of the plane of the board in this case for a right-handed system. So there is a point P with coordinates 0, 0 d, and it's found that the magnetic field at this point is B along the positive x-axis. The magnetic field B is found to be some B times I cap, parallel to the x-axis. Yes or no? We want to find the magnitude of the field as well as the direction of the field. Now, as far as the magnitude of the field is concerned, at a distance d from this wire, the field for a very long wire is going to be mu naught I by 2 pi d, right? So mu naught I is the current divided by 2 pi d. That's of course equal to this B. So the current is known. The current would be 2 pi BD by mu naught. What's not known, whether the current is in the plus J direction or the minus J direction. Right? Now, just examine both cases, plus J and minus J. Suppose the current was like this, going up. Then my DLs would be like this. My R would be like this. Yes or no? And then DL cross R would be like this in the past. Yes or no? See, if these are my DLs, these are the DLs. DL cross R will give me the direction of B. This is DL, this is R. Do you realize DL cross R would be like this if the current was going up? DL cross R would be along the positive x-axis, right? So current is in the positive y direction. Current is in the positive y direction. So J cap you might want to add here if you want to designate the direction of current. If you want to designate the direction of current, yes or no? Is there anyone who wants me to repeat this directional issue, or you're okay with it? Right? Plus J direction. I hope all of you have watched sheet 2 by this time, right? Along the y-axis, there is a current I1. Along the x-axis, there is a current I2. We will assume these are two infinitely long wires, mutually perpendicular to each other, right friends? Now, we want to find the locus of points in the xy plane where the magnetic field, because of the combined effect of I1 and I2, is 0. That's what we want to be able to find. Now, realize that if I looked at a point P, x comma y, means this will be x and this will be y, right? Look at this wire. What's the field produced at P? Mu naught I2 by 2 pi y. And now the direction of this field, because of these are my dls, this is my r, so dl cross r comes out of the plane of the board. So this magnitude out of the plane of the board because of this current carrying wire. Now the magnetic field at this, because of this, is going to be mu naught I1 by 2 pi x. Now in this case, these are my dls, this is the r, dl cross r, this is into. Now the magnetic field at P will be 0 if the field out is equal to field in at an xy, yes or no? So such would be an xy where the net field will be 0, field out is field in, right? So that gives me y equal to I2 by I1 x, which is a straight line passing through the origin and of slope I2 by I1. So the locus of such piece is a straight line passing through the origin and of slope I2 by I1. Clear? Number 6. A long straight wire carries a current in the negative z direction. Okay? This is the plus z direction, negative z direction goes into the plane of the board, right? So just to avoid clutter, this is a long wire carrying current into the plane of the board, carrying current into the plane of the board. Clear? The magnetic field vector B at x comma y in a plane z equal to constant. That's what we want to be able to calculate. See, any plane parallel to the xy plane would have the same value of z at all points on that plane. If you take a plane parallel to the xy plane, that means its distance from the xy plane, which is the z coordinate, will remain the same for all points in that plane. So a plane parallel to the xy plane is going to be designated as z equal to constant. Yes or no? Right? So now at a point xy in a plane with z equal to constant, I want to be able to calculate the magnetic field. Clear? So for example, say this circular loop is part of a plane which is z equal to constant, say z equal to z naught. This is part of a plane which is z equal to z naught. All points on this plane are at z equal to z naught, right? So this point is going to be 0, 0, z naught. This point is going to be 0, 0, z naught, yes or no? Right? And there is a point P in this plane, x, y, and z will be z naught in this plane. At this point x comma y in a plane z equal to z naught, I want to be able to calculate the magnetic field. What do you say? Right? Now, if this distance is r, which is the distance from the current carrying wire, r is root x squared plus y squared. Distance between these 2 points is what? Root x squared plus y squared plus z naught minus z naught squared. So root x squared plus y squared is r? Yes or no? I hope you realize that distance formula. Right? the field at this point, if I is the current, is going to be mu naught I divided by 2 pi r. That's going to be the magnitude of the field, right? The magnitude of the field is going to be at this point mu naught I is the current, divided by 2 pi r, r is root x square plus y squared. Clear? Now the direction of the field. The direction of the field will be given by dl cross r, a unit vector along dl cross r. That means a unit vector along dl cross a unit vector along r. R is this, right? A unit vector along dl, that is dl cap, is what? Minus k cap in the direction of the current. Unit vector in the direction of the current is minus k cap. And r cap is a unit vector along this. Yes or no? What is r cap? R cap would be, what is this vector? X minus 0 I cap plus y minus 0 j cap plus z naught minus 0 naught k cap. So this vector is going to be x I cap plus y j cap plus 0 minus 0 k cap, and a unit vector in this direction is going to be this divided by root x square plus y square. That's going to be a unit vector in along r. dl is like this in the direction of the current. R cap is a unit vector taking you to the point where the field is required, right? So if I calculate a dl cross r, that will give me the direction of B. So unit vector along dl cross a unit vector along r cap will give me a unit vector along B, will give me a unit vector along B. So what is my dl cross r cap? That's going to be minus k cap cross xi cap plus yj cap divided by root x square plus y squared is r. Let me just write it as r. Root x square plus y squared is r, right? Now k cross I will be what? J. K cross I will be j. Yes or no? K cross I will be j. So this is minus of x j cap. K cross j will be minus I. By r. So this is like y I cap minus x j cap by r. Yes or no? You lost? All right now? So then, the B vector at this point, the B at P is going to be the magnitude of B, which is mu naught I divided by 2 pi r into a unit vector along dl cross r, which is this, which is y I cap minus x j cap divided by r. R square is x square plus y squared. So this is like mu naught I divided by 2 pi x square plus y squared y I cap minus x j cap. That's the magnetic field vector at P in general in a plane z equal to constant. At any xy in a plane z equal to constant. Right? All's good? Number 7. A particle having charge Q equal to 10 microcoulombs and mass equal to 3 milligrams has a velocity 10 into I plus 2I centimeters per second. there is a particle, and at t equal to 0 is at the origin. So this is the origin at time t equal to 0. The particle is here, and it has charge q equal to 10 microcoulombs. It has mass equal to 10 milligrams. 3 milligrams? Okay. 3 milligrams. And has a velocity v at time t equal to 0 given by 10 centimeters per second into I cap plus 2 j cap centimeters per second. That is its velocity. That means it has 10 units along the x-axis and 20 units along the y-axis. So its velocity component in the x direction is 10 centimeters per second, and its velocity component in the y direction is 20 centimeters per second. And the whole unit is subject to a magnetic field B, which is given by 0.6 pi Tesla along the x-axis. 0.6 pi Tesla along the x-axis. That means it's subject to a magnetic field like this of magnitude 0.6 pi along the x-axis. Clear? That's one particle. And there is another particle moving with a constant velocity along the negative x-axis in this direction. And at time t equal to 0, its coordinates are 50 centimeters, 0, right? At time t equal to 0, this second particle is at 50 centimeters, 0, 50 centimeters, 0. And it's moving with a velocity, say constant velocity, say v1 in this direction. It's moving with a constant velocity v1 in this direction. The two particles collide, stick together, and the combined mass goes in a circular path. The mass of the uncharged particle, this then is not the charged particle, this is an uncharged particle. So the earlier line which says another charged particle, it must be another uncharged particle. This is an uncharged particle moving along the negative x-axis, right? This particle and this particle, they collide somewhere, and the combined mass goes in a circular path. The combined mass goes in a circular path. We want to find the mass of this particle. We want to be able to find the mass of this particle. Clear? Okay. Now, notice, as far as the motion of this is concerned, it has an axial velocity parallel to B. It has a velocity perpendicular to B. Right? The axial velocity will not change while it moves. Right? It will remain 10 centimeters per second. The velocity perpendicular to B will connive with B to produce a circular trajectory. If this was not there, then 20 centimeters per second and B, they are perpendicular to each other, and they would produce a circular trajectory. Right? Now, also, the plane of that circle will be intercepted by the B lines normally. So if the B lines are in the x direction, then the plane of the circle will be the YZ plane. Right? If this is the Z direction, that's the YZ plane. So this velocity and this B would connive to produce a circular trajectory in the YZ plane. Yes or no? Yes or no? Whereas this component of the velocity will not change, and it will cause axial motion. Right? So the plane of the circle will advance in this direction with time. The nature of motion is going to be helical. Yes or no? Right? Now, in a time equal to one time period, it would come back to the x-axis. That means it would hit the x-axis at instance of time t equal to capital T, 2 times t, 3 times t. These are the instants when it would hit the x-axis, right? At these discrete instants. This particle, however, will continue to move unabated along the x-axis at least till such time that it does not collide with the other particle. Now, if a collision has to occur, the only site for collision then can be the x-axis. That means there are only discrete instants when the collision could take place. Collision could take place at t equal to capital T, t equal to 2t, or t equal to 3t, and so on and so forth. These are the possible instants when the collision could take place. That means in a general sense t equal to n times capital T, right? There are discrete instants, and therefore there are discrete sites where the collision could occur. Yes or no? So first of all, let's get a feel for what the capital T is like, time taken for a full oscillation, which will tell us the instance when the particle will cross the x-axis, right? So let me do a calculation of T. 2 pi m, m is 3 into 10 to power minus 6 kilograms divided by qb. Q is 10 into 10 to power minus 6 into b. B is 0.6 pi. These many seconds, yes or no? 6 pi, 10 to power minus 6. So that gives me 1 second. That gives me 1 second, yes or no? Right? That means the collision could occur at t equal to 1 second, or t equal to 2 seconds, or t equal to 3 seconds, t equal to 4 seconds, and so on and so forth. These are the various instances when the collision could take place. Yes or no? Right? So, of course, not t equal to 5t. Because in a time t equal to 5 seconds, this would have reached this point. But the collision doesn't occur here. So the collision occurs at these instants of time. At t equal to n times t, where n would assume values like 1, 2, 3, and 4. These are the possible values of n. Yes or no? At these instants, the collision would take place. Why not 5t? Because if it was 5t, that means in 5 seconds, it would have come to this point. But obviously, the collision does not take place here. Right? So, now, suppose the collision occurs at t equal to capital T, that is 1 second. Suppose this is one possibility. At t equal to capital T, that is 1 second. Now, 1 second later, t equal to 1 second, this particle would have moved 10 centimeters and this particle would have moved 40 centimeters. Yes or no? Right? So, the site of collision would be 10, 0. T equal to 1 second, the site of collision would be the point t equal to 1 second would be 10, 0. Right? Now, that means in 1 second, this must have traveled 40 centimeters. So then I have knowledge of V1 of the particle. Yes or no? Right? So then V1 is about in 1 second, if this is the site of collision, this is 40 centimeters. So 40 centimeters per second is the velocity of the other particle at the, right? The uncharged particle. Now look, when the collision occurs, particle 1 has a velocity 10 centimeters per second like this. This is particle 1, right? And that's particle 2. Particle 2 has a velocity v1 equal to 40 centimeters per second. Right? Particle 1 in addition has an upward velocity which is 20 centimeters per second at the instant of collision. This is, right? These are the velocity states of particle 1 and this is the velocity state of particle 2 at the instant of collision. Now when they collide and after collision they pursue a purely circular trajectory. After collision they pursue a purely circular trajectory. That means axial motion must have got killed. Yes or no? That means after collision the combined mass, after collision, the combined mass has zero linear momentum in the x direction. Yes or no? Isn't it? After collision, the combined mass has no axial motion. That means after collision, the combined mass has zero linear momentum in the x direction. That means before collision also the combined mass must have had zero linear momentum in the x direction. Yes or no? Yes or no? Right? So then, this mass is 3 milligrams. This mass is, let's say, m0 milligrams. Then, in order that the net linear momentum before collision is 0, we must have 10 into, along the x-axis, 10 into 3 equals m0 into v1. Can I say this? Yes or no? So, 10 into 3, which is 30, must be equal to m0 into 40. m0, so one possibility of the mass is 3 by 4 milligrams. Is one possible value of the mass of the particle. That is assuming that the collision occurred at t equal to 1 second, right? But the collision could have also occurred at t equal to 2 seconds. That means 2 times the time period. Let's then calculate the velocity of the mass subsequently. Yes or no? So, now, see, suppose the collision occurred at t equal to 2 seconds. Suppose the collision occurred at t equal to 2 seconds. Right? Then in 2 seconds, this would have traveled 20 centimeters. The coordinates of collision would be 20, 0. That means in 2 seconds, this would have traveled 30 centimeters. In 2 seconds, this would have traveled 30 centimeters. That means V1 must be 30 by 2, that is 15 centimeters per second. Yes or no? V1 must have been 30 centimeters traveled in 2 seconds. That means 15 centimeters per second. Right? So this time now in the same diagram, V1 at the instant of collision for this particle is 15 centimeters per second. And let's say mass is m0 if the collision occurred at t equal to 2 seconds. Right? Again, the same physics will hold good. The linear momentum before collision in the axial direction must be 0. That means 10 into 3 must be m0 into v1. Same way, right? So that will give me another possibility of the mass. So we have 30 centimeters equal to m0 into 15 centimeters. So m0 is 2 milligrams. Yes or no? Right now? Third possibility is also there. So is 2 milligrams also an option? Yes. Right? Okay. Suppose the third possibility is if the collision occurred at t equal to 3 seconds, then this point would have been 30, 0. That means this mass would have traveled 20 centimeters in 3 seconds. So V1 would have been 20 by 3 centimeters per second. So that would have been V1. So m0 into V1 must be 30 then. m0 into 20 by 3 must be 30. 9 by 2. m0 is 9 by 2 milligrams. That's another possibility. Same way you can look at t equal to 4. So is this also an option? Yes. Right. Same way, repetitive, but only a formality to take care of the last one. At t equal to 4 seconds, this would have been 40, 0. This would have traveled 10 centimeters in 4 seconds. So its velocity v1 would have been 10 by 4 centimeters per second. And then again, m0 would have been 30 divided by 10 by 4, 12 milligrams. Yes or no? Is that also an option? Right. So 12 milligrams, that's an option. So all options, right? These are the various possibilities of the mass of the particle. Got me? Shall we proceed then? A positively charged particle having charge q1 equal to 1 coulomb and mass m1 equal to 40 grams is revolving along a circle of radius 40 centimeters with a velocity 5 meters per second in a uniform magnetic field with center of the circle as the origin. At t equal to 0, the particle was at 0.40. Velocity was along the positive x direction. Let's put together this data. A lot of data. So, there was a particle which had a velocity along the positive x direction v1 equal to 5 meters per second, parallel to the x-axis. And at time t equal to 0, it was at a point 0.40, 40 centimeters from the origin, 0.4 meters, 40 centimeters from the origin on the y-axis. And the mass of this particle was 40 grams. And it was executing a circle of radius r equal to 40 centimeters. And the center of that circle was the origin. The center of that circle was the origin. That's given. Even before I look into the problem further, let's consolidate some relevant data. Let's extract some relevant data and put things in perspective. Okay. See, this particle has a velocity parallel to the x-axis. That means it's moving in the xy plane. It's executing a circular trajectory. That means now the B lines will cut the circular trajectory perpendicular to the trajectory. That means if the plane of the circle is the xy plane, then the B lines must be in the z direction. Therefore, the B lines should be perpendicular to the plane. Yes or no? Right? Now, since the center of that circle, so B lines for sure are in the z direction because the plane of the circle is the xy plane. Right? Now, notice that this is the center. That means this particle of charge q, positive charge q, how much is q given to be? 1 coulomb. Okay. It has its center here. That means it experiences v cross b this way. The centripetal force is given by v cross b. Yes or no? Now, suppose b lines come out. Right? If b lines come out, then v1 cross b realizes towards the center. That means b lines must indeed be coming out of the plane of the board. Otherwise, if b lines were going in, then v cross b would have been upwards. The center of the circle would be higher than this. So b lines are in the plus z direction. Let's first of all calculate the magnitude. So we now know the direction of b. Let's calculate the magnitude of b. Right? Given the radius of the circular trajectory, r is mv1 by qb, will give us an opportunity to calculate b. Right? B then turns out to be m, which is 40 into 10 to power minus 3 into v1 which is 5 meters per second divided by q, which is 1 coulomb, into r, which is 0.4 meters. Yes or no? These many Tesla, so 200 0.5, isn't it? 100. So 0.5 Tesla? Yes or no? So the magnetic field is 0.5 Tesla pushing out of the plane of the board. Yes or no? Right? So this is 0.5 Tesla coming out of the plane of the board. Is that okay or not okay? Now, the rest of the problem, let's see what it says. Now there is another particle with charge q2 equal to 1 coulomb and mass m2 equal to 10 grams. there is another particle with charge q2 equal to 1 coulomb and mass m2 equal to 10 grams. Moving along the positive z direction. See, this is the z direction. Moving along the positive z direction with a velocity v2. See, this is the positive z direction, no? With a velocity v2 equal to 40 by pi meters per second. Collides with this particle at this point, right? And the two particles get stuck. Neglecting gravity and electric forces, we want to calculate the coordinates of the combined particle. We want to calculate the position of the combined particle at t equal to pi by 40 seconds. Right? Clear? Now, when the two particles collide, we can conserve linear momentum along the x-axis, we can conserve linear momentum along the y-axis. Yes or no? Right? So the combined mass has a velocity vx and has a velocity, say, vz. Vx and vz. Right? So, let's say the combined mass is how much? 40 plus 10, 50 grams. Right? And together they have a velocity vx. Vx meters per second, let's say. And that must be equal to the total linear momentum before collision, which is 40 into 5. Right? Yes or no? Right? So the combined mass has a velocity Vx equal to 4 meters per second. That's the velocity of the combined mass in the x direction equal to 4 meters per second. Clear? Okay. Suppose the combined mass has a velocity Vz after collision, right? So then we have 50 into Vz equals the total linear momentum in the z direction is courtesy the second mass. So which is like 10 into 40 by pi. Vz then turns out to be 8 by pi meters per second. Right? Now, let me look at the combined mass. The combined mass has Vx, which is 4 meters per second, and has a velocity Vz, which is 8 by pi meters per second. And the total mass is now 50 milligrams. This is the combined mass, M equal to 50 milligrams, and has 50 milligrams or grams? Grams, right? Grams, right? Grams, and has a charge Q equal to 1 plus 1, 2 coulombs. That's the state of the combined mass. Right? And the whole thing is subject to a B equal to 0.5 Tesla coming out of the plane of the ball. Yes or no? Right? Okay. Now, can I remove the clutter from here? I want to find the position of the combined mass at T equal to pi by 40. Now, look at B like this, which is 0.5 Tesla coming out of the plane of the board. This V and this B are perpendicular to each other, and V cross B is like this, right? This V and this B will execute circular motion in the XY plane, isn't it? Because B lines are in the Z direction, so the plane of the circle executed by Vx and B would be the XY plane, right? Now in the XY plane, the center of the circle will lie here, somewhere here. right? Because V cross B is downwards. Q is positive, so V cross B is downwards. Now, I want to calculate the new radius of the circular trajectory in the xy plane, right? And as far as Vz is concerned, Vz is parallel to B, so it will only produce axial motion. The resulting motion would be a helical path, right? Right? Now, the new radius R nu of the combined mass would be the total mass, which is 50 mv by qb, right? 50 into 10 to power minus 3 into Vx, right? This Vx is causing R, right? Vx, which is 4 divided by Q, which is 2 into 0.5. These many meters? Yes or no? So now this to 200.2 meters. Yes or no? That's a new radius, right? That means now the radius is, the center of the circle will be 0.2 meters from here. This is 0.4 meters. So the new center would be C, and its coordinates would be 0, 0.2, 0. Yes or no? I hope you realize that this is 0.2. That's a new center, right? Whereas Vz will continue to cause only axial motion and will not interfere with whatever is happening in the xy plane. That will only belong to Vx and B, right? This is the new R, which is 0.2 centimeters. Now, so in the xy plane, the combined mass has an omega, which is qb by m, which will tell me the angular deflection with respect to this position, right? So omega of the combined mass is going to be qb by m, angular velocity in the xy plane in the circular disposition. Q is 2 into 0.5 divided by mass m, which is 50 into 10 to power minus 3, 1, so 20 radians per second, right? Is the omega, right? So forget Vz for a while. As far as Vx and B are concerned, this would be the plane of the circle that it will execute with center this, right? Now, the angular deflection in this time, theta, is going to be omega t. The angular deflection is going to be omega t. Omega is 20 radians, pi by 40, so this is going to be pi by 2 radians. 90 degrees of deflection, that means 90 degrees of deflection means the particle was here, it got deflected by 90 degrees. Now at theta, at t equal to pi by 40, the particle would be here. Yes or no? Ignoring the axial motion, the velocity of the particle will be like this. See, the Vx will also get deflected by 90 degrees. Speed Vx will not change, right? This was originally along the x-axis. Now this Vx is in this direction. This also rotates by 90 degrees. If the position rotates by 90 degrees, the velocity will also rotate by 90 degrees. Yes or no? Now, this is 0.4 meters. This is 0.2 meters. This is also 0.2 meters. Now this is the radius, which is 0.2 meters, which means the y coordinate is 0.2 meters. The x coordinate is also 0.2 meters. So the x and y coordinates of this point would be 0.2, comma 0.2. Now we only have an additional task and pretty tension free computing the z coordinate of the particle. The z coordinate of the particle would be Vz into t, isn't it? The z coordinate of the particle will simply be Vz into t. Vz, which is 8 by pi, into t, which is pi by 40, which is also 0.2. So the coordinates of the particle at this instant of time t equal to pi by 40 would be 0.2, 0.2, 0.2. Yes or no? Is that all right? Problem number 9. So there is a circular ring. There is a circular ring. And it carries a current carrying wire. There is a current carrying wire passing through the plane of the ring through the center. Say it carries a current I. Long wire carrying a current I through the center of this ring. Now, there are other current carrying wires, 3 other current carrying wires long, but those pass through the circular ring, pass through the rim, pass through the rim. That means, in one case, for example, there is a current carrying wire I like this. Option A, for example, there is a current carrying wire like this going again, let's say it could be into or out, don't bother about it. And there could be a current carrying wire this way, this way, perpendicular to the plane and passing through a point on the rim, that is the circumference. So in one case they say it's I. In the other case they say it's I, 2I. In the third case it says I, 2I. And in the fourth case it says I, 2I, 4I. These are the various possibilities. Now we want to be able to produce zero resultant on this net force. See, there would be force between these two very long wires. Force per unit length, you know, is proportional to the magnitude of the two currents, right? The separation is the same, d is the same, each equal to radius of the circle, right? There is force between these two, and in the same direction it's going to be attractive or repulsive, and if it's in the opposite direction it's going to be repulsive, right? So one way or the other, in this case, do you realize that if F is the force per unit length between these two, then F will be the force per unit length between these two, F will be the force per unit length between these two also, right? So now can I arrange these three in a manner that the net force on this is 0? Yes. See, if this was F, then this will also be F and this will also be F. It could be arranged in a manner that this is 120 degrees, 120 degrees, 120 degrees, an equilateral triangle constituted out of 3 numbers F and F, and it could produce 0 resultant. Yes. So with I and I could produce 0 resultant. Yes or no? Now the next arrangement of currents is I, 2I, 2I. Okay. Now if this I and this I, the force is F, then this I and this I will also be F, and this I and this I would be 2F. Yes or no? That means now there are 3 forces acting on this, F, F and 2F. Can 3 forces F, F and 2F produce 0 resultant? Yes. F and F like this and 2F like this, they can produce 0 resultant, right? We can produce 0 resultant out of this. Yes or no? Right? So this also is eligible for producing a 0 resultant by, let's say, putting both I and I, 2 current carrying wires like this and the other one 2I like this. I could make sure that the 2 forces cancel each other and they produce no net force. Equilibrium could be produced on this. Yes or no? Right? The third one is given to be I, 2I and 2I. Now, if the force between these two is F, then the force between these two is going to be 2F, and the force between these two is also going to be 2F. Now, can 3 numbers F, 2f and 2f produce equilibrium. If I can create a triangle out of this, then an equilibrium can be produced. Yes or no? If out of three numbers f, 2f and 2f, if a triangle can be produced, then equilibrium can be created out of these numbers. Can I create a triangle out of these numbers? Because sum of any two is greater than the third. Yes or no? So triangle can be created. So suitable orientation of these three along this will cause us to produce equilibrium. Yes or no? Yes or no? The next one is I, 2i and 4i. Now if the force between these two is F, then it's going to be 2F here and it's going to be 4F here. Now, can these forces produce equilibrium? No. See, F, 2F, 4F cannot produce equilibrium because I can't create a triangle out of these because sum of these two is less than the third. So these three forces can never produce equilibrium. So the third set of currents cannot produce equilibrium on this. Is that all right or not all right? Right? Two spherical shells are connected through a long metal wire. Long metal wire means the distance is very large, so there is no interaction between these two. That's what it means. You know what I'm saying? There is no interaction energy of the two. If they are placed at very large distance, there is no interaction between the two. No. When I say interaction means there is no interaction energy. Which means if this wire was not there, then they will not exert forces on each other. The potential on this because of this will be 0. The potential on this because of this will be 0. They will not contribute to each other's potential. They will have potentials because of their own charge, not because of the charge on the other one. This is what I mean when I say a very long wire. Is that all right or not all right? Make sense? Now, the two shells are identical. The two shells are identical means the same radius. That's what it means, right? So, this is radius R, center C1. This shell is also radius R, center C2. One of them carries a charge capital Q at time t equal to 0. At t equal to t1, this is the initially uncharged sphere. This is the initially uncharged sphere and it carries a charge Q. That must be because this would have lost Q. At time t equal to t1, this must be the state. Now at this instant, there is a point P. Somewhere in space there is a point P. And there is a magnetic field at this point, say B1. The magnetic field at this point B1 at time t equal to t1 is this. Okay. Now, just to understand what this would be. First of all, at this instant, there is a current I. This current I would be proportional to the potential difference between the two, right? Current I will be proportional to, now the potential difference between the two is going to be Q minus Q by R minus Q by R. That's the potential difference between the two. So the current flowing at this instant at time t equal to t1, say I1, is proportional to this. That means it's proportional, R and Q are constant, so it's proportional to Q minus 2Q. Now, that's the current I1 at this instant of time. Now, you know, to calculate the actual magnetic field at P, it's going to be very elaborate, very cumbersome because of this current carrying wire, but does not matter. One thing for sure, if the geometry remains the same, then the magnetic field B1 will be proportional to I1, yes or no? That's certain. Biot-Savart law. right? So for sure, B1 will be proportional to I1. Now at t equal to T2, what happens is, this Q becomes Q prime and B1 becomes B2. That's given. So very clearly, B1, B2 will be proportional to Q minus 2Q prime. Instead of small q, it will become Q prime. So Q minus 2Q prime. So we then have B1 by B2 for sure is going to be Q minus 2Q divided by Q minus 2Q prime. What do you say? See, in both cases, the geometry factor of B1 and B2 will be the same. So that will cancel off. So even though it will be cumbersome to find B1, cumbersome to find B2, but to find the ratio of B1 by B2 at two instants is as simple as this. Right now? Huh? Shall we proceed? A particle of mass m and charge q moves with a velocity v along the positive x direction. Right? It enters a region of uniform B along the negative z direction, extending from x equal to a to x equal to b. Say negative z direction goes into the plane of the board. So B lines are into the plane of the board. And say this is the x direction. So it enters this region with a velocity v along the positive x direction. Now this is the region x greater than b. I want the particle to be able to enter this region, and commensurate with that, we want to be able to find the minimum v that can enable this to happen. Right? Now for sure, one thing, v is like this, b is into the plane of the board, so v cross b would be like this upwards. So the center of the circle will lie somewhere here. The radius of the circular trajectory, PC would be the radius, would be mv by qb. And what we are seeking to do is, we want the particle to exit, this is the radius r, we want the particle to undergo a circular trajectory like this, and if it enters with a speed v, it will also leave with a speed v. Why? Because the magnetic field cannot change the kinetic energy. Right? And in order that it exits, for sure, like I've told you, if this angle is theta, this will also be theta. Very clearly, for it to exit, r must be greater than L. R must be greater than L for it to exit, yes or no? To exit, the only requirement is r greater than L. Balo. That means mv by qb must be greater than L. L is b minus a, which will give me v greater than qb into b minus a by m. So the minimum v will be this. This would be the minimum v. This would be the minimum v. Anything in x, if v will become equal to this, then it will go like this and it will have a 180 degrees deviation. Right? And if v is less than this, again pi deflection. Yes or no? Got me? Simple, isn't it? A particle of charge q and mass m enters a magnetic field B making an angle theta with B and velocity V. I mean 12. B lines are like this. This is V at an angle theta. Charge Q mass M. And like I told you, there will be a parallel component V parallel, which is V cos theta, and there would be a perpendicular component which would be V sin theta, and the path is going to be a helical path, yes or no? The time it takes to come back to the original B line is going to be 2 pi m by qb. We want to calculate the total distance that it covers in a full time period t. Vt, absolutely Vt. The total distance covered will, because speed will remain constant, the total speed will remain constant. So distance covered would be simply V into t, where t is 2 pi m by qb. That's going to be the total distance covered. Yes or no? Right? Got it? A positive charge moves in the xy plane at 30 degrees to the positive x-axis. Let's say charge q mass m, and it experiences a magnetic force in the plus z direction. That means like this. It experience plus z direction is like this, right? That means V cross B is like this. That means very clearly B must be something like this, so that V cross B comes out of the plane of the board. Yes or no? And say the angle between V and B is theta. So it experiences a force F, which is QVB sin theta. Magnitude of the force would be QVB sin theta coming out of the plane of the board. Right? Now, in the second case, moving with the same speed, but in the plus y direction. It moves with the same speed, but in the plus y direction. It experiences the same magnitude of the force, but in the negative z direction. That means B is like this, V cross B is this way, negative z direction. Now, very clearly then, what would this angle be? 60 minus theta. This is going to be 60 minus theta. So what's going to be the magnitude of the force? It's QVB sine 60 minus theta, and it's given that these two forces are equal. That's given. So theta must be 60 minus theta. Theta must be 30 degrees. Such is the disposition of B. Right? Now, I have to find a unit vector along B. That will give me the direction of B, a unit vector along B. This is the B direction. Let's say one unit vector along B direction, and this is 30 degrees, right? Oh, this theta is 30 degrees, so this will be 60 degrees. The B lines will make 60 degrees, right? So this is like 1 cos 60 degrees I cap plus 1 sin 60 degrees j cap. Isn't it? It's x and y components. That's this vector of 1 unit magnitude. So which is like 1 plus, which is like I cap plus root 3 j cap by 2. That's the direction of B, a unit vector in the direction of B. Two infinite wires A and B carry currents I1 and I2 such that the movable wire is in equilibrium and the fixed wire B is at a distance r. The two wires are parallel, right? There is a movable wire A and there is a fixed wire B. There is a fixed wire B and there is a movable wire A. And they are separated by an amount r. Right? Now, the mass per unit length of the two is given to be m. Mass per unit length. And they are originally in equilibrium. Now, let's say if I take 1 unit length of this wire, it will experience mg downwards. Now, to be in equilibrium, it must experience repulsion from this. When will it experience repulsion from B? If they carry currents in opposite direction. That means if this carries a current I2, I2 is it? B is I2, like this, then this will carry a current I1 like this. Yes or no? So that the weight per unit length balances the magnetic force per unit length between the two. Now in this case, this is like mu naught I1 I2 divided by 2 pi r, which must be equal to mg, right? That's for sure. Now, this wire, movable wire, is now slightly displaced in the vertical direction. Slightly displaced by an amount much smaller than capital R. I then want to, in fact, I want to show that the motion of A is going to be simple harmonic. And 2, I want to find the angular frequency of oscillation of A, right? So what I do is, let's say this is the equilibrium position for A, EP, right? I displace A by an amount x upwards. I displace A by an amount, small amount x upwards, right? Now, the revised force per unit length is going to be what? Mu naught I1 I2 by 2 pi r plus x. But weight per unit length remains this, and this decreases, so weight then exceeds this. That means this force will exceed this force. That means there is going to be a restoring force towards the equilibrium position, right? So restoring force is going to be mg minus this, is going to be the restoring force towards the equilibrium position. Yes or no? Is going to be, and all of this is force per unit length, right? mg minus mu naught I1 I2 by 2 pi into r plus x. But what is mg? Mg is the original force in the equilibrium position, which is like mu naught I1 I2 by 2 pi r mg being replaced by mu naught I1 I2 by 2 pi r. Yes or no? Right? Which then F restoring, as you can see, turns out to be mu naught I1 I2 by 2 pi x by r into r plus x. R is much larger compared to x, so r plus x is approximately r. So I replace this, and this r into r will be r squared. So do you see that the restoring force is proportional to x, the displacement from the equilibrium position? The motion therefore must be simple harmonic, with this being the force constant, F is k into x, this being the force constant, mu naught I1 I2 by 2 pi r squared would be the force constant of this motion, k, right? The force constant k of the motion is mu naught I1 I2 by 2 pi r squared. The omega would be root k by m. Angular frequency is going to be root k by m. K by m, which is mu 1 I naught I2 by 2 pi r squared into m. Yes or no? Now, notice that mu naught I1 I2 by 2 pi r is actually mg. So let me separate this, so that mu naught I1 I2 by 2 pi r I can write as mg. So mg by mr, g by r, yes or no? Mu naught I1 I2 by 2 pi r is mg by mr, which makes it root g by r. That's the angular frequency. The time period is going to be 2 pi by omega. That's all. Got it? Diptesh? Make sense to all of you? Right? All right, let's look at 15. Panditji. So there is a current carrying wire. And this current carrying wire in 3D space has the equation x minus x naught by L equals y minus y naught by m is z minus z naught by n. L, m and n are direction cosines. This is a line passing through a point x naught, y naught, z naught, and parallel to a unit vector Li cap plus mj cap plus nk cap. Okay. Now, there is a circular loop of radius r. There is a circular loop of radius r centered at x1, y1, z1, centered at x1, y1, z1, and that circular loop lies in this plane. The circular loop lies in this plane. That circular loop centered at x1, y1, z1 lies in this plane. Now, very clearly, a normal to this plane is Li cap plus mj cap plus nk cap, which is a line parallel to the, which is a vector parallel to this line. That means this line must be a normal to this plane. Yes or no? This line must be a normal to this plane. Yes or no? Because a vector along the line is Li cap plus mj cap plus nk cap, and that's perpendicular to the plane. So that means this line must intersect the plane perpendicularly or normally. Yes or no? Right? So the plane that we are talking of is like this. This is the plane that we are talking of, which is intercepted by this line normally. This is the normal to this plane. Right? It's also given that C is minus Lx naught minus My naught minus Nz naught. Yes, absolutely. Yes, yes. So if you plug in minus Lx naught minus My naught minus Nz naught, then this plane is like L into x minus x naught plus M into y minus y naught plus N into z minus z naught equal to 0 is this plane. That means this plane passes through x naught, y naught, z naught. That means, which is also a point on this line. That means the intersection between the plane and the line is x naught, y naught, z naught. So the point of intersection between the line and the plane is x naught, y naught, z naught. How about it? Is that okay or not okay? Now, the circular loop lies in this plane. And the center of that circular loop is x1, y1, z1. So there is that circular loop which lies in this plane. The center O of the circular loop is this point O is x1, y1, z1. And D, as you can see from the problem, is the distance between P and O. D, from the problem, as you can see from the data that is given, D is OP, and it's given that D, if R is the radius of this circular loop, D is given to be much larger than R. D is given to be much larger than small r. That means the circular loop is really small for the sake of calculations, right? Now this circular loop carries a current I1. And D much larger than R, we want to find the torque experienced by this loop. We want to be able to calculate the torque experienced by this loop. Now, one thing. This is a current carrying loop, right? And it has its magnetic moment. Magnetic moment of the loop is I into A, right? And this magnetic moment is exposed to a magnetic field produced by this. So it will experience a torque which is mu cross B. Yes or no? Now, again, as far as its exposure to B is concerned, for the sake of calculations, you can assume that this entire region has a magnetic field, same as the magnetic field at O. Because this is really small, right? All points on this circular loop are practically at the same distance D because R is very small. So the magnetic field at all points on this circular loop would be the magnetic field at O. Yes or no? So I can imagine the exposure to this circular loop is a uniform magnetic field, the magnetic field at O. The magnetic field produced by this wire at O is going to be mu naught I1 by 2 pi D. Yes or no? I. This is I. Mu naught I by 2 pi D. And do you also realize that this B at every point of this would be along the tangent to this loop? Will be along the tangent to this loop, yes or no? That means the B lines lie in the plane of the loop, right? The mu of this loop is like this. So mu and B are perpendicular, right? What's the mu of this loop? That is the magnetic moment of this loop is I1 into pi r squared is the magnetic moment of this loop, right? And mu and B are perpendicular, so the torque is going to be simply mu cross B, which is mu into B into sine 90 degrees. Mu cross B this time is going to be mu into B into sine 90 degrees. So magnitude of the torque is going to be simply mu into B. B is this, mu is this. Yes or no? So the 3D geometry that we just learnt helped. It was more of 3D geometry and less of physics. Okay. I have always believed this, and I've been carrying this notion ever since, I matured, that a physics teacher should first be a maths teacher. Doing physics without really knowing your math right is like not doing justice. So a physicist should first be a mathematician, because he requires plethora of tools at his disposal which comes out of his understanding of mathematics. So you should understand every aspect of mathematics to actually be kind of very exhaustive with your digressions in physics. Otherwise, at some point of time, you would experience a lacuna, you would experience a gap, which would keep widening, and you would keep avoiding certain things because, you ignored your math when you were a kid. You always looked at physics, thinking that equations didn't make sense. Number 16 then. A positive charge is distributed over a circular ring of radius a. Okay. This is a circular ring of radius a, and charge q is distributed over this ring. This is placed in a horizontal plane and is rotated about its axis. This is the axis with an angular velocity omega. A uniform horizontal magnetic field exists in space. Uniform B exists in space. We want to find the torque acting on the ring due to the magnetic force. Again, all that you need to do is a mu cross B. Find the magnetic moment of this and cross it with this. That's going to be the torque. Now, when it's rotated like this, then you can associate a current which is q by 2 pi by omega is the current that you want to associate with this. Equivalent current. Current into pi a squared would be the magnetic moment of this. And the magnetic moment is upwards. Do you realize that? Mu is going to be upwards, and mu and b are perpendicular to each other. So the torque that it will experience is going to be mu into b into sine 90 degrees, right? So that's going to be the magnitude of the magnetic moment, and the torque is going to be mu into b, etc. Yes or no?